Majestic, powerful, immense. For millennia, glaciers have captivated the imaginations of people all around the globe. Glaciers are the result of centuries of snow accumulation and cover nearly 10% of the Earth's surface. Great bodies of ice that flow under their own weight. Glaciers reshape their surroundings, grinding rock and earth into immense glacial valleys, while their own surfaces deform into complex systems of crevasses and seracs. Glaciers' influence on their surrounding environment include climatological and hydrological effects, but their most lasting influence on the landscape is the geological deformations they carve into the Earth's crust as they advance and recede. Quantitatively characterizing glacial flow, then, is crucial to understanding the geological history of the Earth and to predicting the behavior of glaciers as they continue to recede. In this tutorial, we set out to analytically model the flow of glacial ice over the Earth's crust using current knowledge of fluid dynamics and continuum mechanics. This derivation is given in the Physics of Glaciers textbook by Walter, Jovet, Werder, and Lütte at the Geophysical Institute at the University of Zurich. On a microscopic level, glaciers are composed of tightly packed polycrystalline ice particles of various forms and sizes. If stress is applied to a block of polycrystalline ice, the block instantly deforms elastically, and permanent deformation in the form of viscous flow begins and continues as long as stress is applied. Viscous flow is an irreversible process that generates heat and rearranges internal crystalline structure of a block of glacial ice after 1 to 3% deformation. Thus, glacial ice will undergo creeping flow in the direction of its viscous flow under an unbalanced external force, such as gravitational force down an inclined plane. Note that we are modeling glacial ice as incompressible, so there is no net force in the direction parallel to the plane. Before we get started, it is useful to define some of the terms we will be using to describe the flow of ice in a glacier. In continuum mechanics, stress is the force that adjacent particles exert on each other, and can be described using the second-rank stress tensor sigma ij with units of pressure. Strain is the deformation of a body under some external force, and is given by the second-rank strain tensor, which is unitless. From here we can use these two quantities to both describe the internal forces on a section of glacial ice and its relative displacement.
We can derive the velocity of glacier ice by taking advantage of Glen's power law, which relates the strain rate to the stress via a power relationship. Since we know the stress, or can calculate the stress from the field equations, once we have the stress, we can get the strain rate and integrate the strain rate to arrive at our velocity profile.
In order to understand this relationship, it is helpful to define the terms involved. On the left we have the time-varying strain, or strain rate, as the rank 2 tensor epsilon ij. The strain rate is defined as the product of a temperature-dependent constant with the magnitude of the mean stress to the n-1, where n is a material-dependent quantity, multiplied by the second-rank deviatoric stress tensor.
Earlier, we mentioned that we needed to know the field equations in order to calculate the stress. The two field equations we're concerned with are mass continuity and force balance. You may recognize with the bottom form of the mass continuity equation shown, this is simply stating that glacial ice is an incompressible fluid. This assumption greatly reduces the difficulty of our calculation of the velocity profile.
The next contribution to the field equations is the force balance equation, describing all of the forces acting on a given volume of ice. In this case, the forces are the body force due to gravity, B, and the force contribution from internal stress. This equation can be expressed in index notation as follows, or it can be expanded component-wise as shown in the top left corner.
The following recipe, taken from Martin Lüthi at the University of Zurich, outlines the various steps we follow to obtain a velocity profile. First, we determine all components of the stress tensor, using the field equations and symmetries to our advantage. From there, we can calculate the mean stress, which, combined with the components of the deviatoric stress tensor, will allow us to calculate the effective shear stress, tau. Once we have the shear stress, using Glen's power law, we can get the strain rates. Once we have the strain rates, we integrate to obtain velocities, and then, finally, as always, we must take advantage of our boundary conditions to find the explicit solution. It's helpful to draw a diagram of the situation to illustrate our coordinate axes. In true fluid mechanics fashion, we've modeled the glacier as an infinite slab that extends into and out of the plane of the screen. This is the y-axis. The x-axis points downslope, and the z-axis points perpendicular to the slope. U is the velocity of the glacier, which varies with z and is the quantity we're trying to find. H is the height of the glacier, or its thickness. Alpha is the angle the glacier's base makes with the ground. Tau sub b is the basal shear stress, which, as one would assume, points uphill.
This problem has translational symmetry in the x and y directions, and as such no quantities can vary in either the x or y direction. Furthermore, in this model, deformation occurs in the x and z directions, and we assume no deformation in the y direction into the board. Thus, the strain components reduce to a plane strain in the xz plane and constrains all y strain terms to 0. We can apply our symmetry argument to simplify our mass continuity equation down to a single term, varying in the z direction, which we will come back to shortly. Meanwhile, we will finalize our field equations given that there is no gravitational force in the y direction to yield these final equations describing the variance of internal stress. Our one remaining mass continuity term in the z direction implies that Vz is constant throughout the slab, which, coupled with the knowledge that Vz must equal 0 at the base, means that Vz is 0 everywhere in the slab. Integrating our equations for the variance of stress within our ice medium with respect to z yields the following equations for stress, where the constants of integration can be determined with the knowledge that traction goes to 0 at the surface when z equals h. Thus, we can see that stress varies linearly with depth.
Now that I've changed my shirt color, it's time to talk about the deviatoric stress tensor. We talked earlier about how the deviatoric stress tensor does not take into account hydrostatic pressures. Here, from our plane strain condition, we know that sigma IYD, any component involving y of the deviatoric stress tensor, is 0. Also, by definition of the deviatoric stress tensor, the diagonal components, sigma sum xx sub yy and sub zzd, are equal to their equivalent components in the regular stress tensor minus the mean stress. From this definition, and from the fact that, for example, sigma yyD is equal to 0, we can get that sigma yy is equal to sigma m. From Glen's flow law, and from the fact that epsilon sub xx dot is equal to 0, we can see that sigma sub xx is also equal to the mean stress. From the definition of the mean stress, we find that all components of the stress tensor in the diagonal line are equal to the mean stress. Based on the relation between the deviatoric stress tensor and the mean stress, we find that all diagonal components of the deviatoric stress tensor are equal to 0. Furthermore, based on our plane strain condition, the deviatoric stress tensor's components in the x, y, and yz directions are also equal to 0. Additionally, we recognize that sigma xz is not a hydrostatic stress. It is, in fact, a deviatoric stress. These are the equations we will use to calculate the net stress.
The effective stress, tau, can be determined from the components of the deviatoric stress tensor. By definition, tau squared is given as 1/2 of the summation of the magnitudes of the deviatoric stress components. And given that, due to symmetry of the stress tensor, the only non-zero deviatoric stress components are sigma xz and sigma zx, we obtain an effective stress equal to the absolute value of sigma xz, which we have previously derived. Using our deviatoric stress and effective stress, we can calculate the strain rate in the direction of the only non-zero deviatoric stress, xz. Applying both terms in Glen's power law gives us the effective strain rate in the xz direction.
Now that we have the strain rate in the xz direction, we can calculate the velocity as a function of z. We already know that the strain rate is equal to 1/2 del vx del z plus del vz del x. However, we've shown that Vz is 0 everywhere, so our expression is reduced. We can use our boundary conditions to solve for the constant of integration. These boundary conditions state that at v sub x equals 0, which is at the very bottom of the glacier, the velocity is u sub b, the basal sliding velocity. Now we can solve for the single constant of integration.
We now have an expression for the velocity profile of the interior of our glacier, given by the deformation velocity, which varies with z, and the sliding velocity, which is constant.
The approximate shape of this profile is given by the drawing at the top part of the screen. It is important to note that the sliding velocity does not depend on the height of the glacier and therefore is decoupled from our deformation velocity. The temperature and makeup of the bed determine whether or not we can even have basal sliding. For dry bottom or cold bedded glaciers, the base is frozen to the bedrock and our basal sliding term is 0. The glacier only travels by ice deformation. Wet bottom or warm bedded glaciers are lubricated by meltwater and are therefore able to slide over the bedrock or sediment at their bases.
Of course, in real environments, the movement of glacier ice is much more complex than this basic model suggests. But this analytical model serves as a solid first-order approximation for modeling the fascinating dynamics of these massive ice bodies.